PhD degree in electrical engineering from Texas Tech University, Lubbock in 1988. He has worked in industry, academia, and national laboratories developing pulse power and national and modulator systems for a variety of applications, including inertial and magnetic confinement fusion, X-ray radiography, high-power microwave systems, and accelerator applications. Since 2000, he has been with the Spallation Neutron source, Oak Ridge National Lab, Oak Ridge, where he is responsible for installation, testing, commissioning, operation, and ongoing development of a variety of pulse systems. He has numerous papers on pulse power systems and applications. So I'm happy to introduce David, and we can get started with the presentation shortly. I'd like to provide a brief idea of how the session will go forward. David will go ahead and present the presentation and the interesting topic on the electronics at SNS. A lot of us have beat SNS in the past 2 years, and we were very happy to see the electronics that is there within the SNS, and to also look at the different sources that are being developed for the future generation of sources at SNS. And once we have the presentation completed by David, the next step would be we would have a Q&A session with David. For the Q&A session, I would request all our attendees to send in the questions to Shilpa Marti, Rafael Wahda, or Mustaq Mohammed. You can find their names in the toolbox within the chat window, and you can send the questions to them. Once you send in the questions to them towards the end, once David finishes his presentation, we would relay the questions to David and try to get some of the conversation going in terms of the questions that are raised and answer some of these questions that are there. So thank you, everyone. I'd like to thank everyone for joining in. And thank you, David, for being willing to present on this very interesting topic. Over to you, David.
Okay, thanks, Suman. Can everybody see the presentation?
Yep, we can.
Okay, very good. Thanks for the invitation. This is a great opportunity to talk to some local people with similar interests, and so I hope you'll gain something useful out of this talk. As you mentioned, I've been at the SNS now for about 20 years, so I was here during the initial construction, and during the majority of that time, I've been associated with the modulator systems, which is probably one of the most troublesome systems in the whole facility. So we've done a lot of work over the past couple of decades, and I hope to share that with you in this talk. So we'll go ahead and get started. So I just have a list of some acronyms. I won't go over all those, obviously, but they're there for reference. As far as an agenda, I'll start out with an introduction, and then I want to talk about some modern modulators and design options. In the past 10, 20, maybe even 30 years, solid-state devices and the maturation of those has really opened up a wide variety of options for the designer. And so that's kind of cool, because when I started out in this field, a lot of those options weren't available. So we'll talk a little bit about that. Then we'll talk specifically about what we call the high voltage converter modulator system here at the SNS. It utilizes some of these solid state applications for sort of a unique approach, or a unique topology, if you will. Then once you've gone through that, you get a little bit of the background on the system. We'll talk about some of the performance statistics, how we've used some of that information to prioritize and develop and improve the system going forward. We'll look at some of the past failures and some of the upgrades that we've implemented throughout the ensuing years. I want to talk a fair amount about IGBT related improvements, because that's where the majority of the fruitful improvements have occurred. And there's probably some lessons learned for the community in general there as well. Then we'll lead into sort of what the future holds in store for us, which is the proton power upgrade. And we'll talk about a different topology for the modulator systems as well. And then I'll finish up with a summary. So the SNS started in the late 90s. It was a big science project, about $1.4 billion to build the initial construction. It was decided to put it at Oak Ridge National Laboratory. At the time, the Chestnut Ridge was nothing but forest. So it was a green site. In order to sell science of this magnitude back in those days, and I think that's certainly true today as well, collaborations are really important. So we collaborated with national laboratories across the country. You can see down here on the map, all the way from California, all the way up to New York State. And they all had various responsibilities for installation of technical equipment associated with the accelerator. The goal of the facility was to deliver 1 GeV, or gig electron volts, on the target at 60 hertz with a 1 microsecond proton beam. That pretty much captured the the pulsed neutrons spectrum that the scientists were looking at the time, and there was of most interest to them for sort of one of the early pulse neutron facilities in the world. Installation started around November 2002 after the conventional construction was completed, and it took about 2.5 years to get everything installed. We ran the facility at reduced duty cycle up until the middle of 2008, and we took about 2 years after that to ramp up to full power on the target. So I was going to go into a discussion about how accelerators work, but I decided that I'm probably not qualified to do that, and so I'm just going to jump ahead and say that in order to accelerate the beam, we require radio frequency fields in a variety of cavities that are in what we call the linear accelerator, or you'll hear me say LINAC occasionally. Those fields are generated by a device called a klystron. It's basically a very high gain amplifier. And in our application, we use frequencies of either 402.5 megahertz or 805 megahertz. Power levels that we can deliver range anywhere from 550 kilowatts peak all the way up to 5 megawatts. The modulators then in turn are used to power those klystrons. And the klystron efficiencies are rather poor. So a lot of the power is lost in heating of water. So this is kind of a little schematic of what a klystron looks like. See if I can turn this on. So if you see down at the base, what we have down here is what's called a cathode or an electron gun. We heat this up. The electrons are available to be accelerated once you apply an electric field across an anode and cathode. All this is, of course, in vacuum. That electron beam is then accelerated up vertically, in this case, towards the end of the device. Because it's all electrons, space charge tends to cause the particles to want to repel. So there's a solenoid field that retains that and focuses that. We then go through a series of cavities. The first cavity, we introduce a certain amount of power. It's at a relatively low level, somewhere on the order of about 100 watts of RF power. And that begins to bunch the beam. And as the beam accelerates vertically, as it transverses different cavities, it tends to bunch that beam up. And that's how the amplification is achieved. So that finally, by the time it reaches the output cavity, we can get gains that are many tens of decibels. In this case, we go from as much as 100 watts all the way to 5 megawatts. You can see several orders of magnitude. This is an example of what that looks like. This is a particle cell simulation that was done by a klystron manufacturer. And you can see in magenta here the variety of RF cavities. They're all tuned for the resonant frequency that's necessary or desired. And you can see the bunching gets more and more pronounced as one progresses from the left to the right. Finally, at the end, the beam is allowed to blow up in order to dissipate the power into the collector. And that's just to minimize this localized heating so we can manage the heat load associated with that. And there's a picture of one of the klystrons in our facility, which you probably saw in your tour. So for the modulator requirements, we have 15 different systems at the SNS. There are 5 different klystron configurations that we power. Again, 60 pulses per second. We actually produce a modulator pulse that's on the order of about 1 1/3 milliseconds in duration. I mentioned before that the pulse on target is actually 1 microsecond. What we do is, coming out of the LINAC, we chop that beam up into 1,000 different bunches, and we fill what's called an accumulator ring with each subsequent turn. So that allows us to multiply the current by a factor of 1,000 to deliver the required current on the target. The rise time for the modulator is about 150 microseconds. We have an initial flat top requirement of 1%, but because of some problems in the early systems, that was relaxed to about 3%. And the mean time between failure, the goal originally was 24,000 hours with a mean time to repair of 4 hours, excuse me. So you can see down here, peak powers range from as high as 11 megawatts out on the modulator down about 8.5, depending on where you are in the system. And we have anywhere from 1 klystron per modulator all the way up to 11 klystrons per modulator, depending on the load configuration. Here it's shown graphically in what we call our klystron gallery. The first modulator powers 3 klystrons. It's called the RFQ modulator. It operates at about 115 kilovolts. Through the drift tube LINAC portion of the machine, we have 4 different klystrons shown here in blue. Those are powered by 2 separate modulators operating at about 125 kilovolts. Through the CCL section, we actually have a 1-to-1 ratio klystron to modulator, and those operate at about 135 kilovolts. And then when we get into the medium and the high beta section of the superconducting LINAC, the klystron power levels are much lower, basically an order of magnitude. They operate at about 550 kilowatts, so we can get by with powering them to much lower voltage. So modulators really started to get prevalent in the field back around, excuse me, the time of World War II. And a lot of work was done for radar development to protect from the incoming German aircraft on some of the European cities and whatnot. And so a lot of the work early on associated with radar modulators was done over in Europe, of course. Back then, of course, solid-state devices were not mature enough to service these needs because we're producing voltages back then around 20 kilovolts, currents that were tens to hundreds of amperes to drive, in this case, this klystron as well, or actually it was a magnetron in this application. So they use a device called a thyrotron, which is basically a gaseous closing switch. It cannot be opened, so it cannot be turned off. So they had to do some clever things to produce pulses. Later on, as some of the nuclear weapons work developed, there was a need to do some explosives imaging to really understand hydrodynamics. And so this sort of expanded into very large machines that could be on the order of 1 million volts that will produce upwards of, I built machines that'll do 800,000 amps, obviously, for a very short period of time. In our case, it's 50 nanosecond duration pulse, so quite short. But the guys in England were quite creative. This is actually down here below a picture of what's called a spark gap. It's basically a switch that operates at these high voltage levels. And back then there was no commercially available device, so it looks a little deceptive and it's a little hard to see, but there's actually a spoon and a fork that are used as the electrodes. So they had to be pretty creative and come up with unique solutions. And so modulator people are pretty renowned for coming up with unique solutions to interesting problems. So the evolution of modern modulators has progressed since that time. A lot of these are associated with accelerator applications. That's where you see a lot of modulators come into play. This is an early version of a SLAC klystron modulator. SLAC's a lab that was built in the 50s out in California, one of the early accelerators in this country. Again, this used a thyrotron switch, which is shown here down below, but it used what was called a pulse forming network. So this is basically trying to simulate a charge transmission line being discharged through a switch, which can produce a very square wave if it's into a matched load, if you remember your transmission line theory. So this works very well for short pulses, say pulses under 100 microseconds. But once you get much longer than that, it becomes problematic because this employs a transformer and it requires a large number of volt seconds to build a transformer that can support 1 millisecond pulse duration or greater. So once solid state devices came along, the original hard tube approach that I showed in the previous view graph evolved into a version where they utilized, in this case, an IGBT switch. Basically the same concept. You take a large capacitor bank, you discharge it through a switch into your load, and you can open the switch, and so you can create a pulse of variable duration. The problem with the SNS application, because again, it's a long pulse application, is that in order to have minimal droop with this type of technique, we'd require a very, very large energy storage capacitor bank. In this case, it'd be on the order of 1.3 megajoules, which is quite large, and it would occupy floor space of about 25 feet by 25 feet. So that was not very practical, obviously, for us. Moving on, as long pulse became more and more prevalent and there were more and more applications that required it, the people at Fermi, and this was in conjunction with the people at DAISY as well in Germany, developed a technique where they basically, in order to compensate for the droop associated with this transformer over these long duration pulses, they created an LC circuit. And they, by timing and the firing of a switch down here appropriately, the drooping voltage coming out of the large capacitor bank here added to the half sinusoidal wave here compensates for the droop, and therefore they can create a pulse that's quite flat. So you can see without the bouncer in red with the droop, and once you add the bouncer, of course, you get the quite nice flat top shown in blue. So this evolved even further. Now we're getting into the 2000 era, if you will. This was a commercial application that was again developed for DAISY, for a long pulse application they had called Tesla. And this was developed by a company that used to be associated with a klystron manufacturer, but then spun off and was called Amphigon. Now I think it's been bought out again by Talos. But anyway, they've gone through multiple owners. They used something that's a little more familiar to the power electronics folks. They used a series stacked boost converters to create the pulses. And so the concept here was, if you have enough series stacked devices, you can produce any kind of arbitrary waveform, just depending on how you switch the different boost converters in and off and on to create the pulse. And so that is exactly what they did. So this, in this case, there were 20 stages that were just a single quadrant operation, and then a few additional stages that were dual quadrant to compensate for droop effects and whatnot. This was actually one of the first modulator that employed a couple of techniques that are quite useful, and that is one of which is redundancy. So they could add extra modules in here. Not all of them had to work in order to produce the output pulse. So if one were to fail, we could bypass that module and run without it, which is quite nice. And also modularity. So this allows you to swap these modules in and out relatively quickly, which really improves upon the mean time to repair the system. SLAC also, for the International Linear Collider, used a slightly different take on that approach. Here they've done something quite similar. They series stack the outputs together, and they can add as many cells in theory as they like. But in this case, they use one capacitive element, which produces the majority of the pulse, and then they use some series connected buck converters to compensate for the droop. And so those can be stacked. You can add redundancy and whatnot as well. And they use a diode charging scheme. So, they can control the charging through the various diode paths, not only for the main energy storage capacitor portion of the modulator, but also for the buck converter portion as well. Again, this was not available at the time that we constructed the SNS, so it really wasn't an option for us. Subsequently, this company in Spain called HEMA, when ESS was under consideration to be built in Spain, developed a modulator approach, which is, again, somewhat similar. Here, though, they do not use a buck or boost converter on the output section. They actually use an H-bridge, which feeds this energy storage capacitor after a rectifier section, and then they switch those modules in and out. So during the pulse, as it droops, they can play with the phasing of the H-bridge to compensate for that directly, and they do that at the low voltage potential. So that does offer a lot of advantages. This modulator, at the time, the decision was made to build the SS in Sweden. They didn't really have an application for it, so they sent it here, and we actually did quite a bit of work with them to help, characterize and develop and test this modulator. So it actually, in the end, turned out to be quite an attractive solution. And then I mentioned the fact that ESS was decided to be built in Sweden. So a colleague of mine in Sweden decided to sort of take that approach and basically develop it even further. So he is using a series of H-bridges to chop a pulse and driving it through a transformer here. And then he rectifies, filters, and then, of course, connects all these stages in series. So it's sort of a simplified version. The neat thing that he did, though, is because of the Swedish requirements for flicker, harmonics, and power factor, he had to build an active front end. So this modulator, in spite of the fact it runs at 660 kilowatts of average power, has a very, very near unity power factor and very little harmonic and flicker production. So it's quite attractive in terms of from a utility perspective. And then we come to the SNS modulator, which we call high voltage converter modulator. So again, this is a similar technique. We use H-bridges, in our case, 3 of them, 3 phases. Each of those feeds a transformer. It's a step-up transformer. And then we add a capacitor across the secondary. So what we do is we resonate the leakage inductance of the transformer with this capacitor, and we can do some interesting things with that, and I'll talk a little bit more about that here shortly. We then connect each of the outputs of those secondaries to the transformer, the full bridge rectifier. The 3 rectifiers are connected in parallel. We then run it through a filter, and then finally that creates the pulses on the output for klystrons. I'm going to go in a little more in depth on the HVCM, or high voltage converter modulator. This is kind of an overview of the 4 major pieces of equipment. Outside of the SNS facility, you may have seen on your tour these bright yellow boxes. Those are actually the utility power transformers that are associated with the system. So we basically take the 13.8 and step it directly down to 2100 volts RMS. And that's the power that we feed into the building. Once we feed that power into the building, we go into this silicon controlled rectifier 6 pulse system to convert it into a DC power. And that'll allow us to provide power levels just over 1 megawatt of average power, of course. Then finally, after that, once we've created DC, we go into the modulator proper, which is where all the fun is, in my opinion, at least. And that's what this looks like, if you probably recall from the tour. And then finally, we have to have a master control system for all this equipment. So as I mentioned before, we have 15 modulators in operation, plus we have 3 test stands scattered about. And all combined, we're pushing 1.5 million operational hours in all the systems. So Got quite a bit of history on them now. So breaking down each of the major subsystems, this is the power transformer. The power comes in over here on the upper right at 13.8. It goes through a line reactor, and that's the impedance match and provide some harmonic mitigation. Also, because we're driving a 6-pulse system, we create a lot of 5th and 7th harmonics, and we wanted to stay below the IEEE 519 requirement. So we added a 5th and 7th harmonic trap to the system, and it is quite effective. You can see down here with and without the traps. Red is without, and black is with the trap. So you can get up to about a factor of 3 reduction in those harmonics. It is a cask oil construction. There's no oil, which is rather nice, and so it's very low maintenance. These have been extremely reliable for us. All combined with all the systems and all the operational years, there's over 225 years of operations on all these systems. And the only real failures we've had are the Simco fan controller unit, temperature unit, as the touchscreen is faded because of UV exposure, which one might expect in sitting out in the south-facing sun all day long. The next thing, of course, is we take that 2100 volts that comes out of that unit, feed it into an SCR controller. It's a 6-pulse system. This is a kind of a schematic of the basic system itself. Power comes in through here. We have CTs and PTs to monitor the line levels. And then we run through the 6 thyristors. We can generate up to 450 amps at plus or minus 1300 volts with this system. The radiation is less than 2% over from 25 to 100% of full load. And it had some rudimentary control interfaces, but we've since improved upon that in the subsequent years. So this is what it looks like in the business end, if you will. Then we come to the modulator system proper. This is what it looks like. There is a stainless steel and aluminum enclosure. This is where all the devices that are operating in air are located. And that, again, that's primarily for personnel safety. These operate at plus or minus 1200 volts, and we switch currents that can approach 4,000 amps through some of these IGBTs. So there's quite a personnel hazard. Also inside there is a large energy storage capacitor bank in the back, and I'll show you that here shortly. That's where we create our DC link. That capacitor bank is quite large. It can store each polarity up to about 100,000 joules of stored energy. So quite dangerous. And that's what all these sticks, yellow sticks hanging on the side are about. This is to allow us to safely discharge the energy associated with the system. Then this blue tank you see sticking out in the front, that's where all the high voltage components are located. So the power that feeds the primary out of those H bridges actually feeds down through the tank and into the oil submerged components. Also, there's a water distribution panel for cooling systems. There's an oil pump for oil circulation. There's a CO2 system in the back, which you can't see for fire suppression. And there's a variety of diagnostics and controls associated with this as well. So the control system, the early control system that we had was built by a company in Albuquerque, and it actually worked rather well, but it was really limited in terms of the modulation techniques that were available to us to control the IGBTs. Basically, we only had pulse width modulation, and it was pre-programmed to operate over a pretty limited range, and so it really didn't meet our needs going forward. Also, we didn't own the intellectual property on it, and that was problematic, so we really couldn't do a whole lot with it. It also was really limited in the number of diagnostics that were available. So about 7 or 8 years ago, we made a decision to develop our own control system. And we really like this National Instruments Flex Rio system. You can buy these commercial FPGAs and analog and digital I/O and timing cards, and they can be reconfigured for a variety of applications. The sample frequency of the FPGA operating frequency is 40 millisamples per second. So we can get resolution down to 25 nanoseconds, which is more than adequate for our needs. So we utilized all that and built a system with a nice LabVIEW interface, one of the screens of which is shown down here. It all resides in our rack, of course. We've got this HMI interface point here and keyboard control. It's also available through what we call EPICS, which is our remote interface capability, so that this can be operated from a central control room. Not only can we detect events in 25 nanosecond resolution, but if we detect a fault event, we can shut down in less than a microsecond. So it really helps to protect from delivering too much energy into the klystron load and causing it to be damaged. We also can use a variety of modulation techniques, which I'll talk about shortly. Pulse flatten, we can do full waveform capture. Waveforms can be stored in fault events, so we can do troubleshooting later, and a variety of other things which are actually quite nice. So we've kind of gone from the dark ages to something a little more modern, and it's really been really a great advantage to us. So these are the energy storage capacitors I was speaking about earlier. They can operate at plus or minus 1300 volts. We have had really good luck with these. They're a metallized film capacitor, so they fill gradually and gracefully. And we actually go in about every 3 years and do preventative maintenance on them to see if they've reached their end of life. To date, with all the operational hours, we've only had to replace about 10 units, so that's actually pretty good. And then, of course, to bus the power over to the H bridges, we use these parallel RG8 cables. This is what one of the H bridges looks like. It does all the switching at nominally 20 kilohertz. There are 4 IGBTs, 2 on either side of this. All the bus work is in the interior of this. The blue thing you see here is the water-cooled heatsink. And then finally on the outside here is the snubber circuitry. There are also a variety of bypass capacitors. These are about 10 microfarads each. There's a bipolar set of 4 up above, and then there are 8 unipolar ones on either side of the IGBTs. You can see the bus work coming over from the capacitor banks here. These are the gate driver units, and this is the power supply for the gate driver units. So inside of the tank itself, that's where the majority of the high voltage components reside. You can see the transformer here in red. So that's shown schematically over here. This is a step-up transformer, and depending on where it resides in the klystron gallery, it has a different turns ratio. For the lower voltage, you can get by with a slightly lower turns ratio, obviously. Then it is resonant with the capacitor, which is shown in white here, which is shown circled here as well. So one of the reasons we have that capacitor is we can actually achieve some voltage gain. By switching through the H bridge, the large energy storage capacitor, through the leakage inductance of the transformer, you can get a little bit of ring up on this capacitor. And so that helps us get away with not having quite so high of a turns ratio. So that's something we do employ usefully. The rectifier assemblies are shown here schematically, and they're shown here pictorially. Those are large arrays of series connected diodes to hold off the high voltages involved at 135,000 volts in some cases. So that's quite a large array. There's what's called a dequeuing resistor shown here schematically, and it's over here pictorially. That is used to damp the energy in the event of a load fault to keep it under 20 joules, which is kind of what the manufacturer recommends, so that you don't damage that $500,000 klystron. Part of the output filter, which is a pi circuit, consists of 2 discrete capacitors here, which you really can't see in this schematic or this pictorial view. But one of the things we do is we use a voltage doubler scheme. So we pick up a half voltage point and we feed that back to the neutral of these transformers. So that gives us another factor 2 gain in voltage. So we have to, again, employ some pretty clever techniques to pull this off. Finally, there's a choke, which you can see over here, and then that feeds out, of course, to the custom high voltage receptacles that feed the klystrons directly. So some of the components, this is a picture of the transformers. These are developed originally by Los Alamos. This was at the time the largest core of nanocrystalline material. They're about a meter tall, about 2/3 of a meter wide, and about 90 millimeters thick. It's quite a large core, quite expensive as well. And again, we don't design, normally in a pulse transformer, one designs to minimize the leakage inductance to get the rise time as short as possible. But in this case, we designed for a particular leakage inductance and a turns ratio, of course. I mentioned already the rectifier assembly. This is it shown. Each of these cards, if you will, it was a printed circuit board with 6 series connected diodes on it, and they're all lined up in a cassette. So we can have up to 180 series connected diodes per half bridge in this particular application. And that gives us about a factor 2 voltage derating and results in fairly reliable operation. We also put some additional capacitance across this. This helps with the transient voltage distribution when these things are switching and recovering. It also helps with the resonant circuit as well. So performance statistics. So early on, especially when we started operating at 60 hertz, which occurred in about 2008, we had a lot of downtime associated with the modulator. So typically in this facility, this wasn't necessarily true in the early days, but we typically run about 4,500 to 5,000 hours of operation per year. And so you can see that in the early days, we were responsible for about 10% of that time of downtime. which, was nowhere near meeting the 90% availability goal for the facility. So that was a problem. And we worked pretty hard to make a lot of improvements to bring that down. And you can see that, of course, the inverse of that is the availability. And so we now typically operate at around 99% availability for the modular system. So that seems to be capable of supporting a 90% availability goal for the entire facility. That's kind of where we're at the moment. Some of the things we did is we utilized some of the reliability statistics to help us prioritize which major components or subassemblies needed attention. You can see this is a graph over 2008 to 2011. This looks at the improvement in the downtime hours associated with the modulator systems. And this is some of the major things that we implemented during that time. I won't go into a lot of detail, but I will point out, for instance, that I say that we did an IGBT timing change. It was implemented here. If you look at the downtime associated with IGBTs, you can see that it went from about 80 hours prior to that to virtually 0 thereafter. So I think we were on the right track in terms of using this technique to prioritize what we worked on and upgraded, and it seems to work out quite well. However, the downtime events associated with modulators are still dominated by the long duration events. So this is a plot showing all the number of events that occur per run cycle based on the duration of the event. So for instance, the large bars in the turquoise color represent short-term events, less than an hour. And oftentimes these are much less than that. These are the kinds of trips that the system self-resets, but you have to turn the system back on and bring it back up online. So large number of events, but short duration, all the way to the events in orange, which are events that resulted in downtime greater than 8 hours. In the box, you see the number of hours associated with that run period total. And then the percentage in the box is the percentage associated with downtime that's in excess of 4 hours. So you can see in almost all cases, the 4-hour events are responsible for about 3/4 or more of the downtime. And so those are the things that we focused on, and those are the things that we continue to monitor. So now I'll go through some of the upgrades that have taken place since then. One of the early things we discovered was the SCR unit was problematic. This was a unit built by specification by an external company, but we had a lot of problems with it. One of the big things that we witnessed was the fact that the SCRs would fail. And these are some pictures of some of the wafers that we took of the failed SCRs. And you notice a couple different things occurring here. Failure near the gate structure tends to be indicative of insufficient gating because you get very high current densities localized. And you can actually burn the holes through the wafer, and that's indeed what happened. The damage you see around the periphery or the edge of the wafer tends to be associated with over voltage types of events, where it'll actually flash around the edge and cause it to break down. And so that typically tends to be associated with poor snubber design. And so indeed, after the fact that we identified this, we ran this for a little while longer, and lo and behold, we opened up, we had one of the snubbers that looked like this in the blue box. Well, basically the MOVs had gotten so hot because the snubber was not doing its job. This is basically an RC snubber, that the MOVs were taking the majority of the snubber duty, and they weren't designed to do that. So they got so hot the MOV billet actually melted through the case, and eventually it flashed over and turned. So we did a lot of things to improve the drive, the gate drive. We made it a stiffer drive. So this is our design that we added later to the CR cabinet. And actually, we've built more of these with this vendor, and they're actually using our design now. So that's encouraging. Likewise, the snubber resistors originally were a wire wound ohmite design, 225 watt unit. We've since replaced those with a non-inductive version, which is much more robust. And since that time, we've had pretty good luck with the SCR. There have been a few other changes, but I won't go into them. The H bridges were quite problematic early on as well. A lot of that was associated with the IGBTs and or the capacitors. And in some cases, it got so bad, and those of you who work at ORNL probably know this, that we were having the fire truck come up and visit us very often. We would actually have some fires inside of the enclosure. So obviously that was not good, and we had to do something about it. So we started looking into it. One of the things we encountered was that the capacitors were not living up to manufacturer's expectations. So they were, the specification was for them to last 100,000 hours at 3,000 volts of operation. but in our experience, they would only last an order of magnitude less at almost 700 volts lower voltage. So that was not good. What appears to be happening there was that these are a film foil capacitor, when they're wound, they have to be impregnated in oil. And so occasionally you can get some bubbles trapped in there. And it looks like in a lot of cases that some of those defects over time, eventually partial discharge and corona would ensue, and it would actually cause the insulation system to fail. This is actually the inside of one of the capacitors after it had been damaged. And normally the pad, when they wind it's quite flat like this. This one had arced internally and evolved a lot of gases, so basically it kind of ballooned out. That would, of course, cause the case to fail. The case, in some cases, contained a rather flammable dielectric fluid, and so that would drip near the surface, and if arcing ensued, which did in this case, you had an ignition source, you had a combustible material, so obviously you're going to have a fire, and that's what happened. Some of these were also associated with the problems with the IGBT, and I'll talk some more about that later. Shoot through, we didn't have adequate protection was one example of an instance where we would have an IGBT failure. So one of the things we did is we added the CO2 system, which I described earlier, to mitigate some of the fire events. But since we've solved a lot of problems, these are actually rather rare nowadays. So the capacitors, we've evaluated several units, film foil style capacitors from different manufacturers. But in the end, we decided that we liked the energy storage capacitor construction technique, which is a metallized film capacitor. So we actually went back to the same manufacturer. It used to be a company called TPC out of St. Apollinaire, France. They've since merged with AVX, they've been bought out, but they made us this capacitor specific to our application. It's performed remarkably well also. We also are working with a company over in South Carolina, a domestic company called NWL, and we developed a similar epoxy and impregnated metallized film capacitor for us also. And so far, these have really sort of saved us. We also had problems early on with some of the magnetics inside of the tank. In some cases, during a shoot-through event, the Lorentz forces were so severe that we would actually cause the primary winding, which is shown down here in this barbershop spiral configuration, to fail. It would actually arc across the windings, and also it would deform the copper itself. Sorry, I lost my mouse. The winding for the secondary was made by the company that built the modulator. It was a cast epoxy winding, and unfortunately it had air bubbles in it as well. And so we had some instances where it arced through, and there was enough energy involved in the arc to actually crack the case. So finally, we worked with a company out in California, which is famous for pulse transformer development, and we created our own design, which is shown over here on the right. Those have been installed since 2007, and they've actually been running quite well also. So one of the things we did early on is we identified a real problem with some of our SEL modulators, and this has to do with the sort of the safe operating area for the IGBTs. What we discovered is if you look over here on the original design where we had a higher turns ratio, at the time of the IGBT collector current commutation, this is 1,000 amps per division. We were actually commutating currents in excess of 1,000 amperes. And these IGBTs really are not designed to do that in this application. So that would result in failures. So one of the things we did is we looked at using PSPICE type simulations, different turns ratios, different resonant capacitor values to try to bring that commutation current level down. And by reducing the number of turns on the secondary, we're actually able to achieve that. And you can see now that with the current turns ratio, they're actually able to get that level down around 1,000 amps or so. So that's actually quite good. Boost capacitors, these are the capacitors that are across the secondary that make up the resonance. They're a real problem for us. Capacitors do not like to have their potential reversed, particularly at 20 kilohertz. These film foil capacitors do not do well. It really shortens their lifetime. We worked with probably 4 or 5 different vendors initially to develop a solution, and nobody could ever really come up with something that would last more than a few years. A lot of the problems have to do with the fact that in our application, the electric fields internal to the capacitor are quite high because of the proximity to other non-equal potential surfaces throughout the machine. So we would get events where we would actually arc through the case, as shown here and here. Likewise, in some cases, they built it and they didn't do a very good job of controlling the electric fields internally, where they made a connection between the capacitor windings and the terminal, for instance, and so that would enhance the field as well. In some cases, we actually caused tracking across some of the mounting bracketry. So, we worked with all these vendors and we never really found a solution. We did have one company, and they're out of Florida, and they've got a pretty good solution for us. The problem with it, though, is it's an oil compatibility and or maybe even poor thermal welding of the plastic problem. So we don't exhibit any kind of arcing per se, but eventually the case starts to crack. And so right now, what we're doing is replacing those about every 3 years, just as preventative maintenance. We're actually developing now a capacitor array using, again, a metallized film technique. It's a snubber capacitor, again, made by AVX, a series connected array. We've actually run this for about 7,000 operational hours, and it looks really, really good. So we're anxious to take that to the next level. Choke failures have been a problem again. The original design used Litz wires for obvious reason. Unfortunately, the oil did not wick into the Litz wire very effectively. And so there were a lot of electric field enhancements due to the small diameter wires, and we had arcing occurring, and eventually they would fail and open up on us. We since went back to the same vendor that helped us with the transformer design and developed a spiral wound copper sheet winding for the choke, and that's actually been quite robust ever since. Rectifier stacks have been a problem for us, and that had to do with some poor component selection or improper component selection by the manufacturer. In this case, they'd used a metal film resistor, and metal film is really not a very good choice for pulse type applications. This problem didn't manifest itself immediately. It took almost 10 years, but eventually, the metal film failed. Of course, when you've got a large array of up to 180 series connected diodes, once one device fails, then it just redistributes the voltage and just puts a little bit more voltage across all the remaining active devices. But if enough of them fail over time, you actually reach a point where that you can no longer hold the reverse voltage rating of the diode, and then they all go, they avalanche. Another problem we saw was that there were a lot of counterfeit diodes that were actually installed. Some of the good ones that we checked out later, the reverse breakdown voltage was only about half of what the intended devices would have been. So that would have certainly exacerbated the situation. So we've subsequently gone through and replaced all of our normal conducting modulators. So IGBTs, I got to try to hurry a little bit here. It's been a real problem area for us, as I mentioned before. So one of the things we were concerned with was lifetime, because nobody had ever used these IGBTs, the retraction motor devices, in a 20 kilohertz application of this power level. So early on, they did some studies at Los Alamos using the Weapons Nuclear Research Center. This produces a cosmic radiation spectrum that's many orders of magnitude higher than the sun's capable of producing. And they basically applied a DC voltage, and they looked at how long it took for the device to break down. So that actually allowed us to choose the preferred manufacturer's device, which in this case was OIPEC. It's the cyan trace, if you will. We also looked at thermal cycling, and thermal cycling didn't look to be a problem. We're actually off the scale of this chart up above based upon our operating conditions. So that all looked pretty good. So what we recognized early on that one of the problems was the voltage rating. We were running about 70-75% of the rating, which is almost unheard of, because we were using 3,300 volt devices and operating it up to about 2,400 volts of bus. So we looked at a 4,500 volt device, and this was a drop-in replacement basically for us, so the packaging was quite attractive, but these higher voltage devices have much poorer switching losses in this application. And in particular, the West Code device had quite a long collector current tail as well. So these switching losses shown over here are actually at 30 hertz. These are comparable to the switching losses that we see at 60 hertz with our current 3,300 volt, 1,200 amp devices. So that didn't really look very encouraging. We worked with Slack to develop a press pack solution. These had a lot of advantages, and they actually built a switch plate for us using these press pack devices. The problem with it, though, was it would have been quite expensive to retrofit all our modulators to this type of a design. And so while it met all the objectives and the requirements, it did not represent a cost-effective solution for us. So, and then in conjunction with this, we were actually developing snubbers as well. And so that's actually what we ended up doing. So depending on where you are in the switching cycle, you can commutate the current early. So some of the reasons you might do this is if there's a fault detected, you may want to interrupt current early in time, or at the end of the macro pulse. We didn't typically used to complete the half cycle of the IGBT, we just truncated the pulse. So because early on in time, the currents are quite high, and there's enough parasitic conductance in the bridge, that we actually had situations where we could create overvoltage conditions which exceeded the rating of the device, the IGBT itself. So we could get up in the 35, 3600 volt range. And so obviously the devices don't have that kind of margin. So we decided to develop a snubber. Early on at Los Alamos, they looked at an RC snubber, but they had trouble because there was a lot of power dissipated in the resistive element. It was tens of kilowatts. They could not find a solution. So we looked at an RCD snubber incorporating a diode. It's basically a clamp, if you will. And so we evaluated a variety of different diodes, and some of those results are shown down here. You can see that we actually were able to reduce the overvoltage by a factor of 3 in the case of the silicon carbide diodes that we utilize here. So ever since we've installed these, we really had no real problem with overvoltage on IGBTs, and that's after several hundred thousandths of hours of operation. We also developed our own solution for the gate drive. The original gate drive was a sort of a homegrown MOSFET totem pair output stage solution from Los Alamos. We started to work with Slack and like this concept driver, but we wanted to build in some other protection features, so we did that. And that's been in operation for about 10 years, and we subsequently this year are evaluating an improved version of this. That's there primarily so that we can use different IGBTs and also to resolve some obsolescence issues. So if you look at the comparison of the two different drives, this is the original drive shown here, and this is showing single pulse switching losses as a function of operating frequency on the x-axis, if you frequency modulate or frequency shift, and phase shifting on the z-axis. So we were looking at these two techniques as ways to provide pulse flattening to modulate the IGBTs. If you compare that over on the right with the gate drive that we developed, you can see there's a significant improvement in the switching losses regardless of where you operate. So we were able to drop that down by about 30%. Also, because the dead band is less pronounced, you can see that on the RF output, the ripple before versus after is much improved. And so, by about a factor of 5, depending on where you look. So the RF guys are quite happy with that. So this is the effort we did to pulse flatten the output. So if you look here in blue, this is one of the modulators. This is without any kind of modulation occurring. This is the kind of droop we get. It's usually about a couple of kilovolts on the output pulse over the 1.3 or 4 milliseconds in duration. So we looked at two different techniques. One was sweeping the frequency. Here's the gain curve at a fixed EC voltage as a function of the frequency. You can see the peak is right around 23 kilohertz or so. And we've got a pretty good range here. We've got about 2.5 kV of margin or operating range that we can work with. We did the same thing for phase shift modulation with a similar result. The only problem with the phase shift modulation, though, is the losses on the right-hand side of the bridge got to be quite high once you dropped below about 95%. And that was shown in the previous geograph. You could see where that really took off. So we actually ended up just using frequency modulation, and you can see the results here for a couple of cases, the red waveform and the blue waveform over here. So these are really blown up. So that's why, it looks kind of bad, but in reality, it's actually quite good. So those have been in operation now for a number of years, and it's really helped the RF guys out immensely. So now I want to get into the proton upgrade and also the second target station a little bit. I've got a couple of minutes left, so I think we're good. So you probably heard, especially if you work at Oak Ridge National Laboratory, that we are in the process of doing a proton power upgrade for the facility. This was actually envisioned when this place was first constructed. So there was room left in the LINAC tunnel to add more cryo modules. In our case, we're adding 28 new cryo cavities, and so that capability will bring us from what we now have about 1 GeV to about 1.3 GeV. And the motivation behind this is ultimately to do a second target station. However, we can actually leverage this for a first target station. So because of the increased beam energy and because of the increased beam current through the LINAC, we can actually go from 1.4 megawatts on the first target station up to 2. So that opens up some new science opportunities for the Neutron scientists, but it does require us to build a new target. So part of the proton power upgrade project is to develop a new target to support these levels of operation. And here shown, of course, is the second target station, which is going to be the eventual intent. So we're actually, as part of the proton power upgrader, actually building a stub onto our transport line that allows us to tie in and not interrupt operations, so that when the second target station comes online, that the transition is relatively straightforward and does not affect our ability to create science. So what that entails for us is, as I said before, adding some additional cryo cavity, the cryo modules, in the output section of the linear accelerator. There are also additional RF equipment associated with that. We do have to upgrade some of our injection and extraction systems to support the slightly higher energy of the beam and the slightly higher current. And as you can see, a 30% increase in the beam energy, 1.3 GeV from 1 GeV, and a 50% increase in the beam current gives us a factor 2 increase in the power available to the target. So in terms of modulators, it looks like this. This is the far end of the gallery, of the neck tunnel. And you can see the 7 cryo modules and 28 cavities here. Those are powered by 28 cavities, up in the Klystron gallery. And that requires us to add 3 new modulators. And so we really would be pushing the capability of the current modulator with this upgrade. We have to operate, probably another 10% higher in average power. So we started looking at an alternate solution. Likewise, we're also having to apologize for that. We're having to look at upgrading some of our systems in the beginning of the machine as well. So in order to achieve that higher power level of operation, we developed a slightly different variation on the topology of the original modulator. Basically, everything to the left of this line I'm drawing is pretty much the original. And what we did, instead of having the parallel connected outputs, we actually connected them all in series. So each of those 6 phases, if you will, feeds one of these capacitors. We put the capacitor after the rectifier so that the capacitor would not see the ringing that it sees in the current modulator system. So all this has several advantages. First of all, you can see down here that when the IGBT switching, we were turning off under positive non-zero currents. And depending on where we turn off, we actually don't achieve zero voltage switching on the DCE waveforms. With this new design, we get a nice half sinusoidal, because we're basically creating a resonant circuit between the leakage inductance and the capacitor with no ringing, and we get nice clean zero voltage switching as well. So that's actually quite good. It's actually quite a load insensitive, so we can change the load, and it doesn't really affect the waveform shape per se. It only affects their amplitude. So a lot of good things. This is some of the prototype hardware that you see over here, and this is an output waveform that we were able to achieve, again, using frequency modulation only for driving the IGBTs. Another thing we employed is what's called a laminated bus. We did away with the cable bus that I showed you previously. And so we were able to go from a situation where the ringing on the cable bus was shown in red, which was quite high, to using the laminated bus where the ringing was reduced at least an order of magnitude. And so that was quite effective. This was actually developed by a company in Rochester, New York called Merson. And this is one of the biggest laminated bus bars they'd ever built. It's about 8 feet in length and weighs several hundred pounds, so quite impressive. And then finally, the upgrade for the RFQ and DTL modulators, again, because what we call the alternate topology, HVCM topology, was so favorable, we decided to utilize that topology for the upgrade as well. So this is basically quite similar. Obviously, because it's in the earlier part of the machine, it operates at a little higher voltage and a little lower current. So some slight differences in terms of the component selection, but they're basically a carbon copy. So in summary, the modern semiconductors, particularly the IGBTs and MOSFETs, have really ushered in a new era for modulator systems. The HVCM that I just talked about is one of the first long pulse modulators that utilize power electronic techniques at this 1 megawatt level. It currently is supporting SNS phonic operation with a pretty good degree of availability at the moment. The early performance of the system, of course, was not didn't meet the objectives, so we had to make some improvements, and those have been successful. And finally, the proton power upgrade is scheduled for completion in the middle of this decade, and uses this new ATH-VCA. And that is all I have, and here's references for you.
Thank you, David. This was an extremely interesting presentation with actually quite a lot of failure data and failure mechanisms being showcased in detail. This is very hard to get information in general in many power electronics applications. So I'm glad that you could present us with some real world data on the challenges that are faced in power electronics and some of the failure mechanisms that are really observed from your experience. So thanks for that. I think I personally have enjoyed this presentation quite a lot, and I'm pretty sure a lot of our attendees have also enjoyed the presentation. So thanks again.
Oh,
At this moment, if there are any questions, feel free to type in the questions to Mustak, Shilpa, or Rafael. Let me get started with Rafael. Rafael, do you see any questions at your end?
Yes, I have one question regarding high frequency ripples at your slide 53. What's the reason that you have higher switching, higher components and the cable bus bars?
Yeah, let me go ahead and reshare that. Share. Okay, are you able to see it now?
Yes.
So you're referring to this comparison waveform on the right, I presume, correct?
Yes.
So what happens in the case of the cable, normally one associates a cable, if you imagine the current flowing through the center conductor and returning on the outer conductor with a very low inductive solution. Mm-hmm. Because of the bipolar nature of the way we operate the system, we're actually creating a loop, and depending on which phase, if you will, it's connected to, the length of the cable varies. So you actually, in spite of not being intuitive, you actually create a lot of stray inductance in the system. And so that's why you see this ringing. So we have a very large capacitor bank connected to a cable, which feeds each of these H bridges, but each H bridge has a few tens of microfarads of capacitance across it as well. So you create an LCL circuit that's virtually undamped, and that's why you see all this ringing. The laminated bus, the parasitic inductance is orders of magnitude lower, and therefore you still see ringing, and it's still not very well damped, but basically the magnitude is significantly reduced. Does that answer your question?
Yes, definitely, yes. Thank you.
Any other questions, Rafael?
No, not from my side.
All right, moving on to Shilpa. Shilpa, were there any questions at your end?
Yes, there was one question. The question is about how can we predict the aging of individual components? Are they based on any signals available from the measurements, or how do we do that?
So a lot of the components that we purchased from manufacturers were, because this is a relatively new application of this kind of topology, a lot of the data was based on other types of applications. And so they try to utilize some of those studies to project what the lifetime would be in this application. But granted, in a lot of cases, they didn't have data that was specific to our application. So in the case of manufacturing data, it has to be taken a bit with a grain of salt. And in a lot of other cases, we pretty much were on our own. We had to determine what the safe operating areas were for instance, IGBTs, right? We didn't know in the beginning that trying to commutate more than 1,000 amps was going to be problematic. And we just learned that empirically over the years. So it's a good question. I don't really have a good way of answering it. It's just things that evolve over the years based on experience.
Thank you so much. Thanks a lot for the answer.
Any other questions, Shilpa?
No, that was all.
All right, Mustak, are there any questions at your end?
I have two questions here. The first one is, are the failure mechanisms in power electronics like IGBT capacitor, etc., being modeled during the design process and monitored during the operations?
So modeling during the design process, the design was done at another laboratory, and so there was some attempt based on an understanding what the failure modes were with those particular components, yes, but I'm not sure that all the possible failure modes were completely understood at the time. In terms of, well, it's an operation, we do acquire about 32 channels of data continuously. And so we're constantly data logging that, trying to understand and look for trends and variations in waveform changes that might represent some impeding type of failure mechanism. One of the things that I'm particularly interested are looking at techniques to characterize degradation of IGBTs and even possibly predicting imminent failure of those devices. So this is an area of research that I hope to get into in the coming year, for instance. I think that's really interesting, and there are some techniques out there now that will be employed to help with that. So did that help?
I think the question answered very well. I have another question from Craig. At the beginning of SNS, it was desired from the target requirement to track the line voltage phases with the pulses of the facility. I seem to recall these requirements ending up being a problem for both the target choppers in addition to the HVCMs. Can you comment on this?
Yeah, so Craig's quite familiar with the facility, and he's correct. Originally, the timing system for the facility was line sync with the AC line. And that was over concerns about the modulator struggling to track anything that was asynchronous. Subsequently, the choppers themselves, because they're a spinning mechanical system with a lot of inertia, and therefore they cannot respond to changes quickly, the decision was made to try and synchronize with their revolution frequency. And as a result, it turned out that the modulator actually regulated much better than anybody ever suspected. And so we've actually been running in that mode ever since. So we're not line synced with the line, we're line synced with our choppers.
I have one more question. On your slide 38, you are addressing failures in the lead wire. Have you tried to distribute leads wire around the core, not like in layered, but rather in single layer, to have single layer inductor?
So we wanted to try to utilize the core that we had on hand. And they're really, actually, the size of the window wasn't adequate to support the number of turns that were required. You can see here, you can see about maybe half a dozen turns on the outer layer.
Yeah.
Total number of turns on this choke is on the order of 100 turns. So there really wasn't a good way to get a single layer version of it. The problem with the Litz wire, when we submerge it under the oil, we don't put a vacuum on the tank at all. So whatever air is trapped between the different Litz conductor elements has to just work its way out just by by diffusion, if you will. And that really isn't feasible because all the, the spaces are quite small there. And so eventually over time that corona ensues in those locations, and eventually you cause the insulation systems to fail. So going with this flat wound conductor spiral configuration on the right, it really solved all those problems. And it's been quite reliable, so.
Okay. Thank you.
David, I had one more question. I remember you had shown the mean time between failure in one of the slides, the MTBF data.
Yeah,
I think it was for IGBT, if I remember right.
Yeah, I showed the mean time between failure requirement for the system. You happen to know which slide that was off of?
Yeah, I don't remember the slide number exactly, but it's probably somewhere around, somewhere around there. Maybe.
I talked a little bit about the overall system.
Yeah.
I didn't really get into specifics on the. Yeah, is this what you're referring to? This is more about the capacitors in the upper section.
Yeah, but there's one, I mean, there's one slide where you were talking about the NTPF that you had calculated for the IGBTs operating in the modulator.
Yep. So that wasn't total mean time between failure. That was mean time between failure associated only with thermal cycling. Because that was one of the concerns that we had was what's causing these to fail? Was it truly a thermal cycling problem? So I just did the calculation based on the data from the manufacturer and basically came to the conclusion that it really wasn't one of the major contributing factors to the poor mean time between failure. That's really all I'm trying to say here.
Okay. So based on the IGBT failures that you have observed, I mean, that you have tracked at least at SNS, have you seen thermal failure to be an, I mean, thermal cycling to be one of the concerns, especially where you have the bond wire liftoff problem? Is that something that is a concern? And if it is a concern, have you guys been able to map the mean data that you get from the failures that have happened at SNS to the manufacturer's information provided there, the MTBF data that is there of 5.3 years?
So you're breaking up there a little bit. I'm not sure I got the whole question.
Okay. So I mean, the two parts to the question. The first part of the question is at SNS. You've shown that earlier that IGBTs are one of the components that fail, right? I mean, there was at least a higher failure rate earlier. It has reduced since then, but it was still I still had a higher failure rate earlier. Now, were the failures related to thermal cycling?
No, we don't believe they were. We think they were primarily associated with overvoltage conditions across the IGBTs because, you know, that's what all the data indicated. That's what all the measurements indicated. And when we addressed that with a snubber, the failure rate went down by a couple orders of magnitude, I would say.
Okay, so basically more of overvoltage related challenges. All right. So were there any mechanism to identify what's the failure rate with overvoltages? Were they transient overvoltages or were they repeated overvoltages that happened that decayed the device? Did you guys have any information on that?
So we have some data on that. A couple of possible things can happen. One of the things that occurs is whenever an event is detected that requires the modulator to shut down, we shut down very quickly. So that can occur at any point in time during the switching cycles of the IGBTs. And we don't know what the peak current or the collector current is going to be at that time. But if it's high enough, then of course, because of the parasitic inductance in the bridge, you can create quite large overvoltage events. So that's a pretty abnormal condition. We do that though to protect the klystron because we don't want to continue to have the IGBTs pumping energy out to the shorted load. Another thing that happened early on, we no longer do this, but at the very end of the pulse, wherever the IGBTs were in their switching cycle, we would just abruptly turn them off. And so again, that can create a similar situation. We could interrupt a very high amount of collector current and subsequently generate the over voltage condition. And that's what I was trying to show here on some of this early time stuff, say between 0 or 2 microseconds and 8 microseconds, that we created some overvoltage conditions that were quite high. And this was dependent upon location, it was dependent upon operating voltage. There were a lot of variables that went into this. This is kind of a worst case scenario. And then of course, when we added the snubbers and repeated those measurements under the same conditions, that's where we achieved this significant reduction in the overvoltage event. Hopefully that answered. I didn't quite get the whole question because it was chopped up a bit.
No, I think I got the answer that I was looking for. One question would be, I see that your VCE overvoltage that you're showing here, right? It's varying between 0 and 1200 or 1300 volts. When you mean overvoltage, do you mean voltage above 2200 volts?
Yeah, I do.
Okay.
Correct.
All right. Just want to check.
Yeah.
All right. I think I've had quite a lot of questions answered here. Are there any other questions that you have for David?
No.
Okay, David, thanks a lot. Appreciate you providing us with a detailed presentation of the data that is available from SNS on failures and different failure mechanisms, and what the future looks like at SNS. So thanks a lot again, David, for the presentation, and we hope to see you engaged with our group further in future again.
Yeah, when you guys start having live meetings, I'll definitely show up for one of them and meet you all in person. So thanks for the opportunity.
Thank you.
Thank you once again, everyone.
Have a good day.
Have a good day. Take care, everyone. Bye-bye.
Bye.